We're happy to have Ali Zahabi from Bourgogne, and who's going to tell us a very long title from Unitary Matrix Models, Random Partitions, Universality, Multi-Criticality, Engagement. And I hope you explain what all of these words mean to a number theorist. Thank you.
Hi, everybody. First of all, thank you for having me for this talk. As you said, the title of the talk is Unitary Matrix Model and Random Partitions, and we try to explore some universality and multi-criticality aspects in some gauge theories and matrix model. That's my recent work in collaboration with Taro Kimura, which is recently published. And let's look at the outline of the talk. In the first part, we try to review some backgrounds about the problem in gauge theory and how we are going to use the random partitions as some tools to explore the phase structure of the gauge theory. And next, we move on to the main result, which is the asymptotic analysis of the gauge theory. Basically, the phase structure, computing the free energy, and related things using the random partition in the large and limit, which leads us to some results in gauge theory. And finally, if time permits, I try to give you some example of these results, basically. So first, the overview and the motivation. As you know, the partitions are some old topics in the mathematics and mathematical physics. Especially, we know some application like in 80s or 70s of random partition in the 2D gauge theories like 2D Young Mills or in 3 dimensions. And later, after that, there are some application like in supersymmetric gauge theories, the work by Akhundkov and Nekrasov, they are famous works, and also in topological string theory, especially topological vertex formalism. So the main idea is that some gauge theories, so there are some class of gauge theories that we can say that the partition function of the gauge theory is given by the matrix integrals, the matrix models. And the idea is that the sum of a partition is actually related to that matrix model. As we see, it's kind of a discretization of the matrix model. And as we know, the gauge theory might have nothing to do with random objects and stuff like this. But the point is that we can use these methods actually to get some useful information about the gauge theory. A very special point is that actually the powerful technique that the random partition usually brings, especially is the universality aspects, which are related to the random matrix theory. You might have heard about this universality in the random matrices and so on. And so the random partitions are very related to the random matrices, as we will see. And using these techniques, we will get some results which are not easy to get from the field theoretical methods, from quantum field theory methods, and so on. So we will adopt some of these partitions, especially the Schur partitions, and as a special case. And we will see that how that can explain in some class of gauge theory, which is basically the class of Ross-Witten-Wadia models. And we will see how the random partition will explain the phase transition, the famous phase transition in these 2D gauge theories. And later on, we will see some application also about this. So let's move on to the basics of the random partitions. As all of us know, the integers partition is basically a non-increasing sequence of non-negative integers. That is a partition of n, okay, denoted by lambda, which is a sequence like lambda 1 to lambda 7. For example, we have an example of the partitions here. And yes, that is basically this picture, you see. And the total number of the boxes we denote by n. So the partition of n is given by this sequence of number. And in the right-hand side, we have a large partition, which we will see how it will help us to understand the gauge theory. There are some basic aspects about this. We can use the partition as combinatorial labels of some objects so we basically know many examples in mathematics and physics, but especially the group of Sn, the symmetric group of Sn, has this representation given by the partition and so on. But for us, we will see that how the partitions are related to the representation of unitary groups, since we are interested in the unitary matrix models. Okay. That is basically a very basic facts about the partition, but we want to put some measure on the partition to give us some sense of physics, actually. So by defining a measure mu p, which is the Electoral measure, which is basically defined by using the dimension of that representation to the power 2 divided by the total number of boxes factorial, it gives us a probability measure, which basically sums to 1. And also discuss a generalization of that, which is the Poissonized version of this with a parameter q. And okay, that is also normalized by a factor z, which is explicitly given in terms of the q. Okay, so that is basically the simplest measure that we can define on the partition, but one can also consider a generalization of that, which is the Schur measure. As we know, the Schur function appears here in this Schur measure. And the point is that we define, so this is the most important object of this talk is basically the Zn, which we will see that's a partition function of the matrix model, is given by sum over the partitions, which are constraint partitions. So we put a constraint on the first row of the partition, and then we use this weight, which is the Schur measure. And then we have to normalize it by some constant z, which that constant can be again computed using the Cauchy identity. And in this computation, we will get some variables Tn, which are related to the argument of the Schur function xi. So the whole point of this slide is that we define some object on the random partition, which is a Schur partition, and we will see later that it appears in some matrix model. So, and now we want to explain how that is related to the matrix model. First of all, you can think of random partition as kind of a discrete version of the matrix integral. Basically, that is a very natural way, especially the Gaussian matrix is related to this Electoral measure. One can also think about this relation more rigorously, and that is given by the character expansion, which is basically the sum over the constraint partitions with the Schur measure is basically given by this matrix model. So we have a matrix integral with some Haar measure du, and we have the potential, which is given by exponential of some polynomials. So, Here we have a general T bar, but we will constrain ourselves to the case that T is equal to the T bar. You remember the T is the MIVA variable related to the show function arguments. And now the physics is here. So the GWW model, which has this matrix integral representation, the partition function of this model has this matrix integral representation, which has this simple potential raise u plus raise u minus 1 is given by this random partition. And we also considered the generalization version of GWW model, which is given by the Shor partitions. So these are the main object of this study. So we consider a class of matrix model given by these matrix integrals, and we will see that how we can use the random partition in the large parameter limit to explore the phase structure of these matrix models.
Sorry, may I ask a question?
Yes.
Can you just remind us what is Tn in that equation?
Yes, the Tn is basically these. So we can see them as kind of a couplings for the potentials. So, okay, the Tk and T bar k, which we consider them the same, they are kind of a coupling in the potential. For example, for the gross within, we have the coupling which is given by Q. So we move on to the phase structure of the gauge theory. So the point is that we are studying the UN gauge theories basically. The GWW model is a two-dimensional UN gauge theory. So we want to study the large N behavior of this gauge theory, and that corresponds to the large partition. We will see how it works exactly. So we are interested in the study of the asymptotic analysis. In order to study the large partition, basically the main technique is coming from using the Fredholm determinant. So here we have a definition of the Fredholm determinant. You can familiarize yourself with this. Yes, basically that is given by this sum over some integrals of dimension n. And so, okay, the point is that for the generalized GWW model, we have a partition function, and that partition function was given in terms of, okay, some sums over the random partition, which was a Shor partition. Now we want to say that we can express that in terms of a Fredholm determinant with some kernels, which is basically given by KL, and the KZ is given in terms of some J, which are basically some multivariate Bessel function. So we are not going to explain the details of this computation, but the whole idea is that we have a wave function which explains the kernel of the Fredholm determinant. So what we need to keep in mind is that we have the Fredholm determinant, and we will use this formula in order to study the large partitions, actually in the large parameter limit. So let's see, what do we mean by the asymptotic analysis of the random partition? Let's assume the total number of the square in the partition is given by the small n, and the lattice spacing of the partition is epsilon, and the size of the partition, which is basically the length of the first row of the partition, is given by the capital. So now we define a fixed parameter gamma, which is a 't Hooft parameter basically, and we study basically the double scaling limit by sending n to infinity and the lattice spacing to 0. So that is a double scaling limit that we study for the partition. That correspond to sending basically the small n to infinity, which is the thermodynamic limit. There are so many square which are taken out from partition. Okay, so
Sorry, another question. What is lattice spacing of a partition?
it's actually the, okay, we can come back to the basic shape. It is actually the size of the smallest squares. Yeah, so this size, the side of the square actually. So let's consider the simplest case, which is for the Electoral Partition, which there's a typo here. And so when we send basically the n to infinity, we get to the limit shape of a partition given by this formula. That's a famous result by Vershik and Kerov and Logan and Shep. So it's called VKLS shape. So here we see that is this the limit shape of the partition in the large n limit when we do some scaling by a square root of n in these two directions of the partition. So we get to the limit shape, but one can also ask what happens to the fluctuation. What is the distribution of the fluctuations around the limit shape? And so the point is that for the planetary partition, as I mentioned, that is related to the GUE random matrices, and we can think of lambda 1, the largest part of the partition, as the largest eigenvalue of the GUE, and there is a famous result that says that the fluctuation of the largest eigenvalue, which is basically the distribution function of the largest eigenvalue, is given by the TW distribution, Tracy-Widom distribution. So that's a famous result. And now we can mathematically explain that. So the limit of n going to infinity, the probability distribution of the largest part of the partition, lambda 1, has this F2 distribution, which is defined by some Fredholm determinant with the kernel, which is given by some Airy function. And so that is a very important result in mathematics, and we are going to use this to explore the phase structure of the GWW model, for example. So the Tracy-Widom has, this kind of definition, which is exponential of some integral with Q, which Q satisfies the Paine-Levesque second equation. So let me be more fast. As I explained, we use the large parameter limit of the random partition to study the phase structure of the gauge theory. Okay, let's move on to the gauge theory. In the gauge theory part, the point is that, you remember that we had a Zn, which was the partition function of the gauge theory, or the matrix model that we have. We define the free energy as the limit of log of z with some scaling with 1 over a square, which is a normal thing, which is a natural thing. The point is that in the large n limit, we want to say that the contribution to the free energy is coming basically from two parts. First part is actually the normalization factor, which is coming from the limit shape contribution. And the second part is actually the contribution that is coming from the fluctuations around the limit shape, which we claim that is given by this, the log of the Fredholm determinant. So the whole point for us is to compute this fluctuation part, since we know that the fluctuation usually leads to some phase transition in the system. So of course, to this asymptotic analysis, which is coming from the asymptotic analysis of the Fredholm determinant, and especially for this Plancherl measure, we explicitly know what is the kernel of the Fredholm determinant that is given by the Bessel functions, and the Bessel function has some expansion, and okay. We have studied some sort of a scaling limit of this random partition, and let me just tell you what is the result. The result is that the kernel of this Fredholm determinant is in the bulk scaling, which is defined by this, is given by the sign kernel, and actually the boundary scaling is given by the Airy kernel. So, which is a result that we expect actually to get, because we know that the random matrices has the fluctuation, which is given by the Tracy-Widom, and we know that Tracy-Widom is basically Fredholm determinant with the kernel, which is given by this kernel. Yes. So, okay. So now we want to use this result, which is a Fredholm determinant with this kernel, to see how it leads us to the phase structure, for example, for the GWW model. And that is the following. So if, okay, you remember that we define the partition functions by something like this. Now we have a formula for the probability for the lambda 1. Using this formula and this definition of the partition function, we obtained that the partition function of the GWW model is basically by F2 with some argument S. Yes, which is defined by some beta C minus beta and divided by some parameter alpha 2. So, and the point is that the relation between this beta with the coupling in the GWW model is given by this. So beta is like 2T1, and then yes, for this parameter we have this relation, and yes, the gamma, which you remember that was the n times epsilon, we define it as kind of a critical temperature for us. So now what we need to remember is that the Zn is given by F2S, which S is given by this relation, basically. So now the point is that in order to study the phase structure, we have to study the large n limit. So we have to consider the large n limit of F2. And in order to study the large n limit, as we see here, we have the parameter S defined by this. When we send n to infinity, we have two phases, basically. We can have negative and positive here. So for the positive numerator, we get to the right tail of the Tracy-Widom distribution, and that is the limit when S is going to loss infinity, and actually we have the left tail. So we will see that the left tail is actually the strong coupling regime, and the right tail is actually the weak coupling regime. So now we have a formula, free energy, which is given in terms of the log of F2. So as you can guess, what we need to compute is basically the right tail and the left tail of the Tracy-Widom. And using the result by mathematician like Gino Bike, we know exactly what is the behavior of this residuum in the large S, and we have two different behavior in the right and left tails of a distribution. And roughly speaking, we have this behavior. So in the right tail, we get 1 minus some terms of this order, and in the left tail, we get of some terms of this order. So you can see that there are some difference in the behavior of this F2, which basically leads to the physics of the phase transition. So when we compute the F using this result that I told you, we can see that in the weak coupling regime, we get some non-perturbative correction, but in the strong coupling regime, we get some perturbative correction, which has some universality feature. Like this coefficient is always 1/12, and then we have to the power 3. Now we can easily see that there is a phase transition of the third order, since the third derivative of the free energy is actually jumping when we go from the left tail to the right tail. And we claim actually that is GW phase transition. Okay, how do we compare that? We can compare with the famous result by these gentlemen, which obtain the free energy as this in terms of the coupling T, which has the relation to our coupling by this relation. So T is basically 2 times T1. And one can check that the result that I just told you. So this one compared to the result of them by these guys matches up to some good order of epsilon, which is defined by T minus 1. So now we have explained using techniques from random partition that we can reproduce the GWW phase transition. Now you can ask what happens to the general case for the generalized unitary matrix model. You remember that we can have a matrix model which is given by the Schur partitions, which is a generalization of the GWW model. And so the whole story we can repeat. We can do the asymptotic analysis for the Schur partitions. We again do some scaling limit, and then what we obtain is that we get some sort of generalization of what we had before. For example, the kernel that we get in the scaling limit is given by some generalization of the kernel that we had. We call it actually P-Airy. And again, we can obtain the result which are similar to those results. And the thing is that we can, let me just show you the result that we obtain again. Okay. Again, the partition function of the generalized GWW model is given by some Fredholm determinant with some kernel, which is a generalization of the previous kernel. We can compute the free energy as before, and what we obtain is that we again have to consider a generalization of the TW distribution, and what we obtain is actually this results. The first line in this slide, that the Zn is given by this, and the log, the free energy is given by log of Fp. with some argument S, which is given by this formula again. So we have sort of generalization of those. For example, when you put P is equal to 2, you recover what we have discussed so far. And then we can consider a more general case for the generalized WW model with many couplings Tn. Okay, you can turn on and off some couplings in that model. You can compute these parameters beta and alpha, and then you can compute the S. Again, what you need to do is to see what is the behavior of the left tail and right tail of the distribution. And here we have some recent result by some mathematician explaining this behavior. And we have used this result again to compute the free energy of the generalized GWW model, which we obtain this formula for the free energy. Again, in the weak coupling regime, we have some non-perturbative correction to the limit shape FC. And in the strong coupling limit, we get some perturbative result of order 1 and higher orders. And okay, the most important thing here is that we get some phase transition again, which has the order of 2 times P plus 1 divided by P. Sometimes in the literature, they consider the lower bound of this, which is actually, okay, starting from 2 to infinity, we get order 3. But when we send P to infinity, we get a phase transition of order 2. So that's a second order. Again, what we obtain is that, for example, we can claim, okay, from this result, that for the generalized GWW model, when we consider the P is equal to 2, again, we recover this 1 over 12 and the power 3, which gives us a sort of universal phase transition for the generalized GWW model. So what we obtain is actually a universal generalization of that famous result. And we also extend it to some multi-critical cases for the P larger than 2. So we continued the computation. So, okay, we studied the 1 over n expansion. Okay, the genus expansion we computed. So, okay, you can take a look at the paper if you are interested in the details. We also studied the non-perturbative part, and we studied the contribution from instantons in the weak coupling regime. We computed again the contribution from instanton and similar results. Now the last thing in the main part of this work is that we claim that because of the universality, we can claim that in a unitary matrix model class, for a generic potential, we should have similar result. What is different is actually the coefficients here, C1 and C2, which are model dependent. So in that sense, depends on the unitary matrix that you want to study, you get some C1 and C2, but universally what you get is basically the same result for the partition function, which is given by Fp of S, which is the generalization of the Tracy rhythm distribution here. And we have the formula for the S, which is a universal things with some model dependent C1 and C2. So here the power P divided by P plus 1 is universal. Here this power is universal, and here. So, okay, that was the main part, which I'm a little bit over time, but that's fine because what we explain is the main result that we had in this paper. We have applied this result also. Okay, maybe there is no time to explain what is the physical interpretation of this multi-criticality and so on. But let's move on to the gauge theory. Okay, the partition function of, okay, some counting problem in gauge theory, especially for counting in supersymmetric gauge theories, is usually given by this matrix integral, which the potential is given, okay, by this form. It's called relativistic exponential form. The point is that in order to study these kind of potential, we again expect to have similar behavior for the phase structure. Rigorously, we can use some Hubbard Stratonovich transformation to get okay, from the GWW potential, from the generalized GWW potential to this potential, but we can also say that the GWW potential and this potential has the same phase structure. Basically, we can identify the couplings by these. And, sorry. Okay, so okay, the point is that we expect the same phases, okay, phase structure, but the plan is that we are going to study that, okay, more rigorously using some rigorous mathematics. And what we expect is that the Hagedorn phase transition in this sort of model, yes, for example, in the large n limit, the partition function is given by, okay, this formula, and the zeros of the denominators here should give us the singular points, which are the phase transition point for the Hagedorn phase transition. And as we can see here, the WW model, the generalized GWW model basically captures the leading singularities by using this formula that we have for the beta C, which is again the same as the first order here. So, okay, the singular, okay, the leading singular part of the Hagedorn phase transition is the same as the singular point of the GWW model, basically. And then we applied this result in some quiver gauge theory, basically, to compute some supersymmetric, and this is in the free chiral ring, and we use this techniques and result, and then we computed the free energy of this model, and actually we obtained some explicit result for the free energy in the weak coupling and a strong coupling region. So to conclude, I just have reviewed some techniques from the random partition in some unitary matrix model. We explored the phase structure, we explored the universality aspect of the phase structure, and then we can continue by doing some rigorous studies for some concrete examples in gauge theories, and we can extend this to the quiver gauge theories with a multi-matrix model, yes, which is a difficult problem in general. And we want also to consider the complex couplings, which is very interesting in the community. And we will see that how it works in the complex couplings cases and so on. And that brings us to the end. Okay.
Thank you very much, Ali. Are there any questions from anyone? Okay, I have a matter of curiosity. Every time I see 1/12 or minus 1/12, I see zeta of -1. Is that the same origin of that -12 in your free energy?
That is yes, exactly. That is a thing, and you're right. So that 1/12 is actually the coefficient in the left tail expansion of the Tracy-Widom distribution. So if I am that is exactly the zeta. Okay, that's a derivative of zeta at -1. It's here.
Okay.
Yeah.
So that's the zeta of -1, and then you got the derivative in front of it for the other term.
Yes, we have also this. Yeah.
Interesting. I guess Hagedorn has this in buried somewhere as well.
Yes.
Yeah. Very interesting. Any other questions?
I have a comment actually. It's
Yes.
it's that in the applications to gauge theory, when you do your asymptotic analysis,
Yes.
so here you've assumed that Q is a real number.
That's true.
Now, and you said something that Q equal to 1 gives you the sort of singular point where you should focus.
Yeah.
Now, in the applications to gauge theory, it's actually important that Q is not a real number. It's
That's true.
anywhere in the unit disk. In fact, in the gauge theories that you mentioned towards the end, the main physics comes not from Q equal to 1, but from other points on the unit circle.
Yes, there are many saddles, and actually we can consider those, but I'm not sure that how the method we use so far can be extended to consider the complex couplings. But sure, that is a good question to ask. We are also consider this. We are studying this now. Yeah. Yeah.
Great. Good. So we have